A black hole 4 million times the mass of the Sun is flickering at the center of our galaxy like a storm lamp trapped behind 27,000 years of darkness. And the image now racing across the internet is not what most headlines claim it is. James Webb has not photographed the black hole itself because the black hole itself gives us no light to photograph. But Webb has done something almost as unsettling. It has watched the invisible monster change in real time, catching rapid infrared flashes from matter only moments before gravity tears that matter apart. That distinction sounds small until you understand what the telescope actually measured, how close those measurements bring us to the edge of no return, and why the newest data may be more scientifically valuable than another dramatic orange ring. The truth is stranger than the exaggeration. Stick around, because I am going to walk you through what scientists actually confirmed, what Webb really saw, and why researchers studying Sagittarius A-star are genuinely excited without needing to pretend that NASA released the first picture of a black hole. And if you value space stories built from real papers, real instruments, and real uncertainty rather than wild guesses, subscribe to the channel, because that is exactly what we do here. Let's go back to where this story actually begins, long before James Webb opened its golden mirror, and long before anyone had a picture of a black hole. For most of human history, the center of the Milky Way was simply a bright, crowded region hidden behind dust. From Earth, it lies in the direction of Sagittarius, where dense clouds of gas and microscopic grains block ordinary visible light. Looking toward it with a normal optical telescope is a little like trying to see a flashlight through a wall of smoke. You know something is glowing on the other side, but the details disappear. Radio astronomy began changing that picture in the 20th century. In 1933, Carl Jansky, working at Bell Telephone Laboratories, detected radio waves coming from the direction of the galactic center. Decades later, astronomers isolated a compact radio source there. In 1974, Bruce Balick and Robert Brown identified the bright source now called Sagittarius A-star, or SGR A-star. The asterisk was added because Brown considered the object exciting, borrowing a notation chemists used for excited atomic states. But a bright radio source is not automatically a black hole. To prove that something incredibly massive was hiding there, astronomers needed to watch what gravity was doing around it. That evidence came from stars. Beginning in the 1990s, teams led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics tracked stars moving at astonishing speeds near the center of the galaxy. They used infrared telescopes because infrared light can pass through much of the dust that blocks visible wavelengths. Night after night, year after year, those stars traced tight orbits around a point that looked almost empty. One star, called S2 by the European team and S0-2 by the UCLA team, became especially important. It completes an orbit in roughly 16 years. At its closest approach, it rushes around the galactic center at several thousand kilometers per second. Imagine watching a bead whip around an invisible pin, except the bead is a star and the pin contains about 4 million suns packed into a region smaller than our solar system. By applying the basic laws of orbital motion, the teams measured the central mass. The answer kept coming back the same: millions of solar masses concentrated into a space so compact that no known cluster of ordinary stars could survive there for long. A supermassive black hole was by far the best explanation. Ghez and Genzel shared half of the 2020 Nobel Prize in Physics for this work, with Roger Penrose receiving the other half for showing that black hole formation is a robust prediction of general relativity. Yet even after decades of orbit tracking, the central object remained visually hidden. Scientists could see its gravitational fingerprints. They still could not resolve the shadow near its event horizon. To understand why this matters, you have to understand what a black hole image really is. A black hole does not have a glowing surface. The event horizon is a boundary in space-time, the distance beyond which nothing can send information back to us. If light crosses it, that light is gone. So when people say we have photographed a black hole, what we have actually photographed is the bright material around it and the dark silhouette or shadow that the black hole's gravity creates against that glow. That task is brutally difficult. Sagittarius A-star is about 27,000 light-years away, and its apparent size in the sky is comparable to seeing a donut sitting on the moon. No single conventional telescope can resolve that level of detail. The solution was to turn Earth into a telescope. The Event Horizon Telescope, or EHT, linked radio observatories around the world using a technique called Very Long Baseline Interferometry. In simple terms, each observatory recorded radio waves with extremely precise timing. Researchers later combined the recordings, so the network behaved like one virtual dish almost as wide as our planet. In April 2017, the EHT observed two major targets, Sagittarius A-star, and the much more massive black hole in the galaxy Messier 87, about 55 million light-years away. The M87 black hole, known as M87 star, is roughly 6.5 billion times the mass of the Sun. Because it is enormous, matter near its edge changes relatively slowly. That made it the easier target. On April 10, 2019, the EHT collaboration released the first image of a black hole, M87 star, surrounded by a lopsided ring of radio emission. The results appeared in a special series of papers in the astrophysical journal Letters. It was not a James Webb image. Webb had not even launched. Then, on May 12, 2022, the EHT collaboration revealed the first image of Sagittarius A-star, based on those 2017 radio observations. Again, this was not Webb. The image showed a dark central shadow encircled by glowing gas, broadly matching Einstein's general relativity. It was historic, but it was also an average built from many possible images because the source changed while researchers were observing it. Here's the detail that tends to stop people in their tracks. Gas around M87 star can take days or weeks to complete an orbit near the black hole. Around the far smaller Sagittarius A-star, comparable motion happens in minutes. Trying to image it is like trying to take a long exposure portrait of a puppy chasing its tail in a dark room. During the exposure, the subject never stops moving. That was the old limitation. And that is exactly what James Webb was able to attack. Webb launched on December 25, 2021, and began science operations in 2022. Its primary mirror spans 6.5 meters and is made of 18 gold-coated beryllium segments. The telescope operates near the Sun-Earth L2 point, about 1.5 million kilometers from Earth, where its giant sun shield keeps the instruments cold. Unlike the EHT, which studies radio waves, Webb is an infrared observatory. Its job is not to replace the Earth-sized radio network. Its job is to see a different layer of the same physical event. The pivotal turning point came when Webb's near-infrared camera, NIRCam, stared at Sagittarius A-star for extended periods and measured its brightness simultaneously at two infrared wavelengths, around 2.1 and 4.8 microns. This was crucial. Instead of collecting only a static view, the team built a time record, a light curve, showing how the emission rose and fell second by second and minute by minute. It had exactly one chance to do something no ordinary photograph could do. It could watch the black hole's environment breathe. The findings were led by Farhad Yousefzadeh of Northwestern University, with observations involving NASA's James Webb Space Telescope and analysis published in the astrophysical journal Letters in February 2025. The team examined roughly 48 hours of observations collected across several sessions during 2023 and 2024. Webb did not reveal a quiet point. It found a source that was almost never still. The first major finding was continuous flickering. Sagittarius A-star appeared to produce a steady stream of small brightness changes, with no obvious stable resting level. The light rose, dipped, trembled, and surged. According to the research team, the behavior may come from turbulence in the accretion flow, the thin, hot, magnetized gas moving around the black hole. Think of cream swirling in coffee, except the fluid is plasma heated to extreme temperatures, moving through intense gravity and threaded by magnetic fields. Tiny magnetic disturbances can twist, reconnect, and release energy. In solar physics, magnetic reconnection helps power flares on the sun. Near a black hole, a similar process may accelerate electrons until they radiate strongly in infrared light. In simple terms, Webb may be watching magnetic weather beside the event horizon. But the flickering was not just random visual noise. The pattern changed across the two infrared wavelengths. In several events, the shorter wavelength emission peaked before the longer wavelength emission. The delay was measured in seconds to tens of seconds, depending on the flare. That time lag matters because energized particles lose energy as they radiate. Higher energy electrons tend to emit at shorter wavelengths first. As they cool, the emission shifts toward longer wavelengths. It is similar to a piece of hot metal changing color as it cools, although the underlying physics and wavelengths are different. So the first discovery is not simply that the center of our galaxy flashes. Astronomers already knew Sagittarius A-star produced flares. The advance is that Webb can follow those changes continuously and in multiple infrared colors with extraordinary sensitivity, giving researchers a direct test of how particles are being heated and cooled near the black hole. That is real. It is measurable. And honestly, it is more useful than pretending Webb photographed darkness itself. If you appreciate this kind of correction, where the actual science turns out to be just as dramatic as the viral claim, drop a like. It helps factual space content reach people who might otherwise see only the exaggerated version. There is a second discovery, and it makes the scene more violent. Webb detected both faint, rapid flickers and much brighter flares. The small variations may be produced by turbulence, while the larger events may require stronger magnetic reconnection, magnetic field lines snapping into a new arrangement and dumping energy into nearby particles. Researchers do not yet have a final model that explains every flash. That uncertainty is important. Science is not weakened when experts say, "We are still working this out." That is the process working correctly. Some models picture temporary hotspots orbiting close to the black hole. Others emphasize shocks or reconnection events inside a chaotic accretion flow. A hotspot moving around the black hole could brighten and dim because of relativistic effects. When the emitting material moves toward us, its light can appear boosted. When it moves away, it can appear weaker. The black hole's gravity also bends the path of the light, allowing us to receive radiation that traveled around the curved geometry near the event horizon. In other words, the flicker may encode motion. A changing point of infrared light can carry information about orbital speed, magnetic structure, particle temperature, and the shape of spacetime. The image itself looks modest, a fuzzy bright source amid a crowded field, but the time series behaves almost like an electrocardiogram for the galactic center. And then there is the third finding, the one that tends to unsettle people the most. Sagittarius A-star may look calm compared with the spectacular quasars that blaze across the distant universe, but it is not dormant. It is active on small scales all the time. Our central black hole is a relatively light eater. It is not currently swallowing enough material to power a brilliant quasar. The Milky Way's core is not blasting a luminous jet across intergalactic space like M87. Yet Webb's observations show persistent energy release. The environment is continually changing, even during periods we might casually describe as quiet. That forces astronomers to rethink what quiet means around a black hole. A city seen from orbit may look motionless at night, but zoom in and you find traffic, electricity, weather, and millions of separate events. Sagittarius A-star is similar. On the scale of the whole galaxy, it is subdued. Near the horizon, it is restless. The data also connect with another historic result. In March 2024, the Event Horizon Telescope collaboration published a polarized image of Sagittarius A-star in the astrophysical journal Letters. Polarization is a property of light that reveals the orientation of electromagnetic waves. By mapping it, researchers inferred strong, organized magnetic fields spiraling near the edge of the black hole. Sarah Issoun of the Center for Astrophysics, Harvard and Smithsonian, and Angelo Ricarte of the Harvard Black Hole Initiative were among the project leaders. The magnetic structure around Sagittarius A-star looked surprisingly similar to the structure previously seen around M87 star, despite the enormous difference in mass and activity between the two systems. That comparison suggests strong, ordered magnetic fields may be a common feature of black hole accretion. Webb's flickers and flares now give scientists a way to watch those fields change with time, while the EHT maps structures close to the shadow in radio light. One telescope gives you the outline, another gives you the pulse. And this is why Webb working alongside the EHT is more powerful than either instrument working alone. If a flare occurs during radio observations, Webb can mark when it began, how it evolved at different infrared wavelengths, and how quickly the particles cooled. Researchers can then compare that timeline with changes in radio structure. They are not merely making a prettier image. They are trying to build a physical movie of matter in extreme gravity. Drop a comment and tell me which result surprises you more. The fact that the galactic center flickers almost constantly, or the fact that magnetic structures near two radically different black holes look so similar. I am genuinely curious where your instinct lands. Now picture for a moment what it would be like to hover near Sagittarius A-star, far enough away to survive in our imaginary scene, but close enough to sense the scale. Behind you, the Milky Way would no longer look like a pale stripe across the night sky. You would be inside its crowded central region, surrounded by dense star fields. Bright blue giants and red supergiants would burn through curtains of dust. Gas clouds would stretch across space in glowing arcs. The radiation environment would be fierce. Ahead of you would be no solid sphere, no cosmic drain with a visible surface. You would see a warped region of darkness surrounded by light from hot plasma. Some photons would travel almost directly toward you. Others would loop through curved spacetime before arriving, bringing distorted views of material that is physically behind the black hole. The accretion flow would not behave like a smooth ring in a textbook diagram. It would churn. Magnetic fields would twist through the plasma. Electrons accelerated during a reconnection event would suddenly brighten the infrared sky. A flare might rise, peak, and begin to fade while matter races through a significant fraction of an orbit. Then, the longer wavelength glow would answer moments later. That delay, mere seconds measured by an observatory 1.5 million kilometers from Earth, would tell scientists that the particles were cooling. Something happening near a boundary from which no information can escape would leave a timed sequence in Webb's detectors. You would not be seeing the black hole, you would be seeing everything the black hole forces the universe around it to do. And that distinction is the heart of this story. But that was just the beginning, because Webb's black hole work extends far beyond the center of the Milky Way. The telescope is also changing our picture of how supermassive black holes formed in the early universe, and those results may be even more disruptive. Before Webb, astronomers already knew that enormous black holes existed when the universe was young. Quasars, powered by billion solar mass black holes, had been observed less than 1 billion years after the Big Bang. The problem was time. How do you start with a black hole formed from a dead star, perhaps tens of times the mass of the Sun, and grow it into a monster millions or billions of times more massive in only a few 100 million years? Feeding has limits. As material falls inward, it heats up and radiates. That radiation pushes back on incoming gas. A black hole can sometimes exceed the standard limit, but sustaining extreme growth is difficult. Scientists therefore proposed heavier starting points. Direct collapse black holes formed from enormous gas clouds, or perhaps even primordial black holes created under exotic conditions in the very early universe. Webb is now finding objects that let researchers test those ideas. In May 2026, NASA, ESA, and the Canadian Space Agency announced detailed Webb observations of Able 2744-QS01, a tiny red source seen as it existed roughly 700 million years after the Big Bang. The object is gravitationally lensed by the massive galaxy cluster Able 2744, also called Pandora's cluster. The cluster's gravity magnifies the background source and produces 3 images of it in the sky. Using NIRCam for imaging and the integral field unit on NIRSpec for spectroscopy, the team mapped the motion and composition of gas in QS01. An integral field unit is essentially a device that collects a spectrum at many positions across an object, allowing astronomers to build a chemical and velocity map instead of one blended measurement. The researchers measured gas moving under the influence of a black hole with a mass of roughly 50 million suns. According to the ESA Webb release, that black hole may account for about 2/3 of the system's total mass. The host is only around 1,300 light-years across, tiny compared with the Milky Way. Roberto Maiolino of the University of Cambridge and Ignace Georgebalis were among the researchers discussing the result. The gas appeared dominated by hydrogen and helium, with very low levels of heavier elements. Its metallicity, the astronomers' term for elements heavier than helium, was reported at less than about 0.5% of the Sun's value. That is a remarkably primitive environment. The interpretation is still being debated, but the evidence suggests the black hole may have formed before a substantial galaxy developed around it. That reverses the familiar sequence in which stars form first, some stars collapse into black holes, and those black holes later grow through feeding and mergers. Instead, QS01 may represent a black hole that began with a heavy seed and then helped assemble a galaxy around itself. Notice what Webb has done here. It has not photographed an event horizon. The source is far too distant and too small for that. It has done something different. Separated faint infrared light, measured spectral lines, mapped gas velocity, estimated a central mass, and tested the chemical maturity of the host. This is where the phrase real image can become misleading. A real scientific image is not always a literal snapshot that matches human eyesight. Webb's images are built from measured infrared photons assigned visible colors. Spectra can be turned into maps. Velocity can be shown with blue and red shades. These are not fake. They are translations of real data into forms our eyes and minds can understand. The EHT image of a black hole shadow is also reconstructed from radio measurements gathered across Earth. It is not a conventional phone camera photograph, yet it is direct observational evidence, rigorously tested through independent imaging methods. Science does not become less real because instruments see differently than we do. If this explanation helps separate the image from the measurement, share the video with someone who has seen the headline but not the context. The fastest way to fight bad science communication is not to mock people for clicking. It is to give them a better story once they arrive. So, what does all of this actually add up to? First, the headline claiming that James Webb produced the first real image of a black hole is wrong. The first black hole image was released by the Event Horizon Telescope on April 10, 2019, showing M87 star. The first image of the black hole at the center of our own galaxy was released by the EHT on May 12, 2022. Second, Webb is contributing something the EHT alone cannot provide. Its infrared sensitivity allows it to track flickers and flares from hot material around Sagittarius A-star, often at multiple wavelengths at the same time. Those variations reveal how particles heat, cool, and move through magnetic turbulence close to the black hole. Third, Webb's observations fit into a wider multi-wavelength effort. EHT polarization measurements show organized magnetic fields close to the shadow. Infrared timing traces rapid energy changes. X-ray observatories can detect the highest energy outbursts. Radio telescopes follow cooler material and horizon-scale structure. Combined, these instruments move us from a frozen portrait toward a dynamic model. And fourth, Webb is discovering and measuring black holes across cosmic time. In the early universe, objects such as Abell 2744-QS01 challenged the assumption that galaxies always came first and black holes grew later. Some black holes may have started large, perhaps through direct collapse, and may have played a central role in building the first galaxies. Researchers are still working out which formation path is correct. Primordial origins remain speculative. Direct collapse models face their own unanswered questions. Mass estimates and host galaxy measurements will improve as more observations arrive. That uncertainty is not a loose end added for drama. It is the actual frontier. The transformation from the opening is now complete. We began with the claim that Webb had finally taken a photograph of darkness. What Webb has really captured is change, a stream of infrared signals from matter being heated, accelerated, cooled, and rearranged by gravity and magnetism at the center of the Milky Way. A still image can show us where the shadow is. A changing light curve can begin to tell us what is happening around it. That may be the deeper breakthrough. The black hole at the center of our galaxy is not a distant illustration or a mathematical symbol. It is a physical engine operating right now, 27,000 light-years away. The flashes Webb recorded have already completed their journey across the galaxy. They left the galactic center when human civilization was still far in the future, crossed dust clouds and spiral arms, entered a telescope built by thousands of people, and ended as tiny electronic signals inside NIRCam. From those signals, scientists reconstruct seconds of violence near the edge of forever. And perhaps that is the most honest image of a black hole we can ever have. Not the darkness itself, but the universe bending, heating, and flickering around something we are forbidden to see. The storm lamp from the opening is still there, hidden behind 27,000 years of darkness. Now we know its trembling light is not a trick of the camera. It is matter sending one last message before the abyss takes over. Subscribe and turn on notifications because Webb, the Event Horizon Telescope, and the next generation of observatories are still collecting data, and the picture will keep changing. Leave a comment with the black hole question you want scientists to answer next, share this with someone who enjoys the real mystery more than the exaggerated headline, and keep looking up. Thanks for watching, and I will see you in the next.